This webinar is going to cover topics pertaining to measurement risk and provide the participant with some tools necessary for implementing TUR, risk assessment, and guard banding using ANSI, NCSLI, Z540.3 methods 5 and 6. There is an alternate method on the Excel spreadsheet that you can get after the webinar as well if you would like to use that method. Little bit about myself. My name is Henry Zumbrun. I'm the president of Morehouse Instrument Company. Here's my contact information. It'll be on the PDF. If you have any questions afterwards, questions tomorrow, the next day, whenever, please feel free to email me or jump on our website if you have any interest in some of the products, adapters, or other training courses we offer. So start off with a little thing, why measurements matter. This is pictured on the right is the Swedish warship Vasa, which famously sank in 1628, less than a mile into its maiden voyage. It was discovered that it was built asymmetrically. So what effectively happened is archaeologists found 4 rulers used by the workers. 2 turned out to be based on the Swedish feet with 12 inches. The other 2 used Amsterdam feet with 11 inches. Seems kind of silly. There's a lot more information. You can go search Wikipedia on this. It's a pretty interesting whole scenario on how they built this grand ship for the king, and a mile in, it sinks. And then later they define, probably the reason it sank is the measurements. Things probably did not go together too well when you're using a different standard of length measurement. Then we go to another one, the link videos on YouTube. This one's really interesting. This is Lake Penor, November 20th, 1980. An oil rig contracted by Texaco accidentally drilled into the diamond salt crystal salt mine under the lake. They later found, they think because of an incorrect or misinterpreted coordinate reference system, the rig with coordinate system set up backwards, and the 14-inch drill entered the salt mine here to the right, entered the salt mine, and basically that 14-inch hole turned an entire freshwater lake into a saltwater lake, and the force was so strong it started pulling from the nearby river. And it actually pulled, I think, 7 barges in, and over the next 2 days, those barges just started popping out. Very, very interesting scenario. It's YouTube video is a little old and dated, but it's pretty cool on what can happen or when things go bad. So, little forward there as people were coming in. The agenda today, what Morehouse does. That's going to be real quick. The new ISO standards come out. It's been released in November. We're going to talk about test uncertainty ratio and what this means. Method 5 versus method 6, measurement risk, and then 3 steps to reduce your measurement risk practices that you can put in place to help. So, and then again, just to reiterate, if anybody has any questions during the webinar, please type them in and I'll answer them at the end of the presentation. So for those who do not know what we do, Morehouse is a manufacturing company that produces force calibration equipment and adapters that are used in industry to measure force. We have a state-of-the-art force and torque calibration laboratories and offer calibrations at a very high level of accuracy. Force capability here, that's a 120,000 pound dead weight machine. That's a primary standard in accordance with ASTM E74. So we have the capability at a primary level up to 120,000 pounds. Then we do other measurements up to 10 meganewtons or 2.25 million known to within 0.01% of applied. That is our CMC that will go into a TUR calculation that we will discuss. So, and then our torque capability, we bought our torque machine from an NMI, a National Metrology Institute. We bought them from NPL. We actually have the second most accurate torque calibration standard in the world, accurate to 25 parts per million. And that goes to 2 kilonewton meters. So those are the 2 things. So let's talk about risk management. The laboratory has to plan and implement actions to address risk and opportunities. The laboratory is responsible for deciding which risk and opportunities need to be addressed. Simply, a new standard comes out. One of my good buddies said the best way to implement this standard is just go through section by section of the new standard and apply this formula. It was a recommendation. I don't know what auditors are going to look for yet. We don't know that. It's just come out, but pretty much each section is going to have a part where you can go through and say, hey, my risk equals my probability times the impact of occurrence. So, and here's a picture of a collapsed bridge. Obviously, someone failed to figure out something. The impact, severe. If they got one of these things wrong, what did they do wrong? There's various sources that say different things, but they could get things that they could get wrong. They could get incorrect concrete strength measurement. They could get incorrect steel strength measurement. They could maybe not have checked their cables properly for pre-stress or post-tension. So my thought here is, if my impact is high, I should probably not use the most inexpensive calibration supplier who may not meet my needs. It could be adapter issues. It could be oxidation of things. Whatever it was, someone did not get the risk level right, or they would have prevented it and taken care of it. So some things you can do, some tools you can use. We're not going to discuss these in this hour. This is a full day course. You can go. A2LA has great training. You can go with them. They have great stuff. Fishbone diagram, fault tree, failure mode and effect analysis, process failure modes and effect analysis, 5 whys. There's also 8 Ds: team, problem correction, RCA, corrective action, implement and validate, prevent reoccurrence, closure. Like I said, a lot of the ABs, specifically, I get the training from A2LA, offer this type of training all the time. You know, days, 2-day classes, 3-day classes. There's also an excellent class on risk taught by Scott Mims. If you happen to see that and want to take it, I highly recommend it. So, going back on topic to our standard risk management in 2017, if we compare 2005 to 2017, 2005 is manage risk, policies, procedures, job descriptions, top management, quality manager, maybe a technical manager, all of this stuff composed in that ISO IEC 2005 standard. And then 17, the new version, seems to move away a little bit from this, and it's more focused on risk and opportunity. Management requires documented info, processes. Decision rules are finally there. They were kind of there in the 2015 or 2005 standard, but now they are very, very clearly defined. And what they did is in 2017, they took away a lot of the should references and replaced them with shall, and you'll see that. I'm going to go through some examples of things that have changed or things that are new. So there's a 5.5.c document its procedures to the extent necessary to assure the constant application of its activities and validity of the results. That one is a new statement. And then we have statements such as 6.4.5, which says the equipment used for measurement shall be capable of achieving the measurement accuracy and or measurement uncertainty required to provide a valid result. We have 6.4.6 that say when the measurement accuracy and the measurement uncertainty affect the validity of the reported result or metrological traceability is required, measuring equipment shall be calibrated. And then it goes further on to say 6.4.7, the laboratory shall establish a calibration program which shall be reviewed and adjusted as necessary in order to maintain confidence in the status of calibration. 6.4.9, equipment that has been subjected to overloading or mishandling, gives questionable results, or has been shown to be defective or outside specified requirements shall be taken out of service. It shall be isolated to prevent its use or clearly labeled or marked as being out of service until it has been verified to perform correctly. ASTM E74, which is a 4 standard, has a section on if it's overloaded, it needs to be recalibrated. This is essentially saying the same thing there. It's good measurement practice, if you think something has been overloaded, mistreated, is to take it out of service immediately until you have it checked and verified. 6.5.2, the laboratory shall ensure the measurement results are traceable to international system of units. So basically, I'm so happy for this. All of those reports for the last 5 years that those of you who know are in the metrological world, everybody says I need traceable to NIST. That is a bad statement to make. It is a wrong statement to make. It is traceable to SI units. You can say I need traceability to SI, and I would prefer you to use NIST, but when everybody goes around and lists NIST traceable, that's not necessarily a good thing anymore, and people are moving away from that, which is the correct thing to do. And this is basically what that means. Traceable to SI units starts at SI units. Typically, these are the BIPM. up here. SI units, everything's traceable back to the fundamental SI units. Then you have your NMIs, National Metrology Institutes. You have your NIST, your NPL, your PTB if you're in Germany, your CNOM if you're in Mexico. These usually have the best standards in the world. Not always. Our NMI NIST happens to be the best at everything it does. So if we look at this for force, the standard uncertainties NIST is about 4 to 5 parts per million. And then we have primary reference laboratories such as ourselves, Morehouse. We run around 8 to 50 parts per million. And then accredited calibration suppliers, of course, are down 0.025%, working standards 0.1%, and field measurement is 0.5%. So essentially, this is what it means, traceable to SI. And if you notice this, the uncertainty gets larger the further you are away from the true SI unit or the further away you are from the NMI. So then the new standard talks about risk management decision rules. A laboratory performing calibrations, including of its own equipment, shall evaluate the measurement uncertainty for all calibrations. I think ILAC P14 addressed this fairly well. So most people should, if they're complying with P14, hopefully they're in compliance already with 7.6.1. 7.8.4.1, the measurement uncertainty presented in the same unit as the measure am or term relative to the measure and each %. So if I'm doing a report in pounds force, I need to report in pounds force or %. I should not report my measurement uncertainty in divisions or in kilonewtons or in some unit that I'm not using. So that one's pretty straightforward. 7.8.6.1, when a statement of conformity to a specification or standard for test or calibration is provided. This is new. The laboratory shall document the decision rule employed, taking into account the level of risk, such as false accept and false reject, and statistical assumptions associated with the decision rule employed, and apply the decision rule. The last 510 in the old standard said it was a statement of compliance. Now we're at a statement of conformity and we're going into decision rules, and that's where we're going into. There's several decision rules. We're going to talk about method 5, method 6 today, specifically because we have that document, ANSI Z54, NCSLI, ANSI Z540. .3. We have that document in the appendix that we can follow. And then we have 7.8.6.2, the laboratory shall report on the statement of conformity such that the statement clearly identifies to which results the statement applies, which specifications, standard, or parts thereof are met or not met, the decision rule applied, unless it is inherent in the requested specification or standard. So we're going to talk about this. So what are risk management decision rules? Well, if we go to ANSI NCSLI Z540.3, section 3.5, measurement decision risk as a probability that an incorrect decision will result from a measurement. We look at the new ISO standard, section 3.7, defines a decision rule as a rule that describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. This graph on the right shows this. Basically, we have our tolerance, and then we're going to draw this graph here. We're going to draw this graph. And anything to the left right here and anything to the right of our line is our risk. So basically that is all measurement risk. And this line is based pretty much based on the bottom line, the uncertainty. And we'll go over what exactly it's based on. So what this does, what this means, if you see a certificate, so risk management decision rules. Here's an example of one of our certificates we've done for a customer. We have the acceptance limit. These are not guard banded limits. So this standard acceptance limit right here on these columns. You could see guard banded limits here. They're not. Expanded uncertainty listed. TUR, and if you look, a lot of people like TUR to be better than 4 to 1. It's not in this case. So since it is not, we are reporting the probability of false accept, and as long as that probability of false accept is less than 2%, we can say the instrument passes. So compliance, pass, fail. We are saying this passes 3.23 to 1 TUR, PFA, and we're going through all of this, all of these. The other way we could issue this cert is we could have the adjusted accepted limits and pass it as long as they're within the adjusted acceptance limits. So there's different ways you can employ this or do this. So, but this is what we're doing for now. We are writing a new program to do both method 5, method 6, and some other things. This is we're using method 5 in this scenario. Measurement related terms, test uncertainty ratio. So we talk about TUR. That last cert had an example of TUR. It is the ratio of span of the tolerance of the measurement quantity subject to calibration to twice the 95% expanded uncertainty of the measurement process for calibration. So simple formula right here, TUR is the unit under test tolerance divided by the calibration process uncertainty. What is actually in this denominator here? Well, here, this slide's going to show you what's in that denominator. So you have your tolerance up top, and then your denominators, typically your calibration and measurement capability of the lab divided by the appropriate coverage factor, raised to the, squared, the unit under test, the resolution of the unit under test, and the repeatability of the unit under test. That's the long formula. And we're going to multiply this to the appropriate K factor that gives us, in this case, it's about 95% confidence. We're using a 2, but you may want to, some people may want 99, they may want to use something else. So this is the basic formulas for TUR. That one at the top is the one that we use, in the PFA sheet. If we're calculating TUR, we're going to use that. It will allow you to change your coverage factor. It will allow you to do lots of different things. I've seen this also written this way, and I don't like this one, but because it's assuming the 4, but in any case, and then the denominator, what are we looking at in the denominator? We're looking at multiplying the standard uncertainty by the appropriate coverage factor for whatever our 95%, 99%, whatever the confidence level needed, and using the appropriate coverage factor. So then resolution of the UT, and repeatability of the UT. So if we look at this, we're looking at this formula, and we take our TUR versus a typical force lab. This is our dead weight machine versus an automated cal machine on the right. Both instruments, we have a 10,000 pound device accurate to 0.05% of full scale, resolution of 0.01 pounds, and 0.05 pounds of repeatability. If we look at this equation, Morehouse CMC, 0.02% of applied, one-sided tolerance 5 pounds, expanded uncertainty 0.22, TUR of 22 to 1. So we go over to a typical force lab, and they're operating around 0.05% of applied, not 0.16. We have, in this scenario, an expanded uncertainty of 5 pounds and a TUR of 1 to 1. What does this really mean? Well, I'm going to show some pictures of what this means and the impact that it may have. So, but the question is, we look at the new standard, section 6.4.5, the equipment used for measurement shall be capable of achieving the measurement accuracy and or measurement uncertainty required to provide a valid result. Do you think a 1-to-1 TUR is going to allow that? And the answer is really maybe. We don't know until we actually look at the graphs or we look at the specification limits, and then we offset those by a certain method, or we take the uncertainty into account in method 5. So in this example, this is graphically, in this example, the instrument read 10,000 pounds when 10,000 pounds was applied. That's up here if you're looking. You can follow this measured value up here. So we're saying we applied 10,000, it read 10,000. Our risk, this is telling me a 1-to-1 TUR. The risk is greater than 4%. It's telling me a 1-to-1 TUR in this scenario is not good enough, that I need a better calibration provider than the lab that can do 0.5. Now, maybe I only need a lab that can do 0.4 to get that in. So we have to look at this in greater detail. So if we look at these two graphs and we say, hey, I read 10,000 when 10,000 pounds was applied. What if I move that location of the measurement to 10,004? This graph right here is going to move over, and this graph right here is going to move over. And what effectively is going to happen is when we slide that over, our lab, Morehouse, with a TUR of 22.7273 to 1, can still say this instrument passes. This instrument is in tolerance. The secondary laboratory that's performing this calibration, that's, you know, 05, even if they were 025 or 02, they're not going to be able to say. They have the risk right here increases pretty drastically, and it goes from, you know, 4.55 to 34.47. So this is really what you want to pay attention to when you're doing, you know, how much room do I have? You know, some labs can depending on the resolution, that denominator, depending on the resolution and repeatability, some labs with a 1-to-1 can say units intolerance, but they can't if it goes anywhere almost out in this scenario. If it goes, you know, 10,001, they're not going to be able to say it's intolerance. They're not able to say it's intolerance at 10,000 in this specific example. So, you know, we start looking at when TUR does not matter, then we're talking about TUR and how it gives you more room on each side. But if I'm at my specification limit, I don't care what lab in the world is doing the calibration. If the specification limit is plus or minus 5 pounds and we get the instrument in and we report 5 pounds, even with a 22.72 to 1 TUR, the total risk is what the new standards, you know, they're talking about reporting PFA, which is probability of false accept. The total risk is still 50%. So people forget this. They say they get caught up on, I need a 4-to-1, I need a 10-to-1, I need whatever. But here's what really what it amounts to: a 4-to-1, 20-to-1, 100-to-1, 1,000-to-1 TUR does not mean anything if the instrument is right on the tolerance limit. In this example, if the instrument read 10,005, the PFA would be 50% with a TUR of 22.73. If we had a TUR of 1,000-to-1, it would be 50%. The only thing that happens is this 50% can get larger if this graph is so wide that it encroaches the lower specification limit as well. And that could happen. If you're dealing with 1-to-1 TURs, sometimes you'll have, when you're on the limit, you'll have total risk of greater than 50% when it's on the limit with 1-to-1 with 1-to-1 TURs. But essentially, that's TUR matters to some, in it gives you a much larger envelope where you can still call the instrument good. So the picture I like to show with this is to say the larger the TUR, the more room you have. See this car in this spot? You know, if I start approaching, if I move this car over to the left and start approaching the line, chances are I would hit the door. At some point, you know, if I put this car on the line directly in between it, I'm into the other car. So I can't do that. I can only slide the car up to this line, and at which point I'm giving myself less room to open my car door. So I equate it to opening car doors in parking lots. You know, you use a lab with very low uncertainties, good quality standards with high TURs. It gives you room to the left and to the right. More than likely, you can freely open your door without banging the car door beside you, if you think of it in those terms. Use other labs that do not have as good of TURs. You may need to, you know, suck it in, get up, suck it in, kind of shimmy so you don't, you know, bang the car door beside you, or you may be completely into that car door or on top of it in some regard when you're looking at like 33% hanging over the line. So you just can't park there. So this is why evaluation of the labs and their TUR still has a lot of merit, but know that if you're on the specification limit, it does not matter what your TUR is. It will always, when you're on the line, be 50% or above. So calculating risk. Some people can say, oh, I have 3 years to implement the new standard. You know, I don't need to do it. Well, you know what? 17025 2005 section 510.4.2 basically says, no, you should be doing this now anyway, because it says when statements of compliance are made, the uncertainty of the measurement shall be taken into account. This, to me, this is applying a guard band. You have to, it's just not telling you, like the news section is telling you that the laboratory shall document the decision rule. And right here, 7.8.61, the laboratory shall document the decision rule employed, taking into account the level of risk such as false accept and false reject, and the associated rule and apply the decision rule. So this is no longer vague. This is very straightforward, and you're going to be reporting, the probability of false accept. And if you're a lab, the other thing we haven't really talked about is the probability of false reject, which means you're saying an instrument's bad when it's actually good, so you're adjusting it on the lab side. But I'm more concerned for this of the false accept and showing that, hey, even though I had a lab with 100 to 1 TUR, if they reported that at 10,000, if my specification limit was such that I'm right on the line, I have a larger risk than I thought. So we get into this in greater detail, the two methods. There's method 5 guard bands. So we have method 5 versus method 6. These are the two I'm saying, hey, they're in ANSI C540.3. They're very easy to implement. There'll be more that come out with the new standard. People will be promoting different ones, different ways to do things. But these two are very simple to calculate, so we can discuss these. They're simplest guard bands to calculate. They're calculated only from the measurement uncertainty. The test limit is based on the worst case PFA that will be accepted for any individual measurement. Disadvantage on method 5 is there is a high probability of false reject because they may be too aggressive. Then we look at method 6 guard bands. These are simple to calculate as they depend only on measurement uncertainty when compared with specification limits of the unit under test. So method 6 guard band formula is as such. We calculate acceptance limits based on that 2% that I mentioned earlier. And we define those limits. So any point, if I have any point that falls within those two measured limits, I'm good. It's basically calculating my acceptance limits. The problem with method 6 is you need to alter the formula a little bit. It does not work with TURs that are above 4.5. When you stick a TUR in here of above 4.5, basically what happens is this formula allows the acceptance limit to go beyond the specified tolerance. So what we've done in our Excel sheet here is if the TUR is above 4 to 1, if it's 20 to 1, we've just written a simple formula that says use a TUR of 4 to 1 for this formula. So your acceptance limits, so it works properly. It would have been an easy fix for them to add. I don't know why they didn't add it, but here's the graph to the right here, and it's just something to be aware of with the formula. So here we have our TUR sheet, PFA. I call it the PFA sheet. Again, anybody can get this after the webinar. They'll get an email and they can download it. Here's two samples, method 5 versus method 6. In this sample, the CMC is 16 parts per million. Method 5 here, the total risk with method 5 is showing that the last 3 points of this calibration are out. Whereas if we go down and we use, method 6, we're showing that the total risk, our acceptance limit, is such that they would still be in tolerance. Down here we have the pass, but that's showed on the next sheet. So here's what's happening. Method 6 limits shown here. Method 5 limits shown here. These are very tight when using method 5, so the instrument is failing at the last 3 points. And it shows that method 5 is really more conservative. If you use it, you're going to fail more than you would with method 6. So in this scenario, we're using 0.0016. We put this in our dead weight frame, did the calibration. What happens if we go to the next calibration supplier down, that accredited cal supplier? Same data sets, nothing else has changed except for the calibration supplier. Well, in this scenario, this supplier would have to fail both methods because of that, because of their uncertainty. So produce failures for both methods. So if we raise the tolerance of the UUT, we had the tolerance on that last slide at 0.5%. So we send it to the secondary calibration supplier. They can't pass it. The only thing that's left to do is essentially accept a raised tolerance. You want 0.5 percent of full scale, but you get 0.1% of full. If you raise the tolerance, then things can pass, and that's what this slide shows an example of. So it's something to consider. If your cal provider cannot issue the proper statement, that maybe you can raise the tolerance on your equipment. Don't know. So we start to talk about measurement risk. I have questions to ask. Many of you, it's have you or any of your technicians ever overloaded a load cell? This is for space. Have you or someone you know ever used the wrong equipment to try to accomplish a certain task? How about your calibration provider? Have they admitted to ever making a mistake? If the problem was not corrected, did it just go away? Let's face it, none of us are perfect, but we can mitigate measurement risk by making better measurements and replicating the proper use of all instruments to lessen the possibility of devastating errors. We can go through and we can say, hey, risk probability times impact. What's going to happen if this happens? If my impact is huge, some things that we cannot control, maybe cannot control. FedEx, UPS damaging the shipment inbound. Even if we pack it to the best of our ability, sometimes they're going to drop it, and it's going to create a problem. But we can control the risk level going out of our organizations because we can make sure they're packed right and packed well, that maybe they can survive a 3-foot drop. These are things we can think about, and if it makes sense to do it or not do it. You can go through the probability times the impact and say, hey, if this goes bad, we're going to have an angry customer and that impact is high. Or you can say we're going to have a bad measurement and that impact's even higher. So 3 things you can do to lessen your measurement risk. I mentioned earlier there's a 2-day class on measurement risk. Scott Mims gives it. He uses a 3-legged stool example. I love his example, so I'm using that here. If you take away any one of these 3 legs, it's really difficult to sit on the stool. So 3 things you can do: know the right requirements, choose the right equipment, and have the right process. And if we look at these individually, know the right requirements. The first rule involves knowing what is needed to accomplish the task at hand. The more accurate the system, the higher the cost will be to procure the equipment and have it calibrated. That's pretty much common sense. If you're going for the utmost uncertainty, you may have to go to NIST for calibration. There may be no one else. You may have to accept the 1-to-1 TUR if you're using certain standards that are the same as what the NMI in the country uses. Lots of times that's the best you can get is the NMI in the country, or you can go outside. For most tests, a TUR of 4-to-1 will meet the guidelines set forth in ANSI Z540 of ensuring the total risk is less than 4%. This is what I said. In most cases, that 4-to-1. If you are at the tolerance limit, it will not, and that's what you need to know. So everybody that says 4-to-1, this and that, if you're at that tolerance limit, it's still no good. So if the requirement is 0.1% of applied and the stability of the device is 0.2% over a 1-year period, the device would have to have the calibration interval shortened. We see this a lot here. And I try to address this with customers. And what essentially happens is they say, hey, I want this device to be 0.1% of applied, adjusted if it's not in. Every year it comes in, it's not in calibration. At some point, some auditor or someone else should look at this and say, hey, what you're claiming is wrong, because the stability of your device, every single time it goes back, it's adjusted. If they would just up their tolerance to 0.2%, they're probably not going to have adjustments, and most likely they're going to be in that tolerance for the stability period between recalibrations. But people forget about that all the time. They just look at what is it at the time of cal, 2 years, a year, 6 months, it comes back. If it's not maintaining that tolerance, guess what? You need to raise that tolerance. So some things, this is what happens when Rule 1 is not followed. This is the BP Texas refining moments before and immediately after the explosion. This was happened March 20th, 2007. In a 335-page final report, federal investigators from U.S. Chemical Safety Board, CSB, concluded that organization and safety deficiency at all levels of the BP Corporation caused the March 23rd, 2005 explosion at the BP City refinery. So what happened? The accident, distillation tower attached, down drum overfilled, 7,600 gallons of flammable liquid was released, and that was ignited by idling diesel truck. We had some things happen such as high level alarm malfunction, level transmitter miscalibrated, outdated 1975 data sheet. Level transmitter actually indicated the liquid level was falling when it was actually rising. These were things that could have been easily prevented. So, and then you dig you dig deeper into it. You have cost cutting, production pressures, and failure to invest. Hey, this happens. What your organization gets acquired by another organization, sometimes they come in and they cut costs. BP acquired Texas Refinery, so maybe they came in and cut costs. I do not know. Lack of preventative maintenance and safety training for sure. And then what happens when you don't have the right equipment? When I said, the right requirements, when you don't have the right equipment or the right things, guess what? People develop procedural workarounds to compensate. It happens in every organization. If you're not doing the right thing, people want to do the right thing, they're going to develop a workaround. It could be with lab equipment, could be with adapters, could be with test leads, could be with lots of different things. So at this, the cost, 15 deaths, didn't need to happen, 180 injured, and over $2 billion, including lawsuits, probably for what would be, several $1,000s to get the right equipment in there, maybe tens of thousands, I don't know, but certainly not $2 billion. And that's if you take Scott Mims's risk course, he'll talk about this and lots of other cool examples. So rule number 2, choose the right equipment. Always choose measuring and test equipment that is capable of achieving the measurement tolerance required. Pretty simple. People fail to do it though. If you need to certify that an instrument is within a tolerance of 1%, you really can't use a standard with a tolerance of 1%, because you know what? That TUR formula, if you're 1-to-1 on this is, and then you start plugging in repeatability, and you start plugging in the resolution of the device under test, you're no longer 1-to-1. And several manufacturers just do not understand TUR, and even on a 1-to-1 level, they think it's okay that they can go use a 1% device to go certify 1% equipment and then give it to their customers and say it's all good. So on most of these instruments, no reference standard in the world may lower risk if the instrument shows any bias. Choosing the right equipment also includes choosing the right adapters for your system. So when I say that on most instruments, no reference standard in the world, here's one. Here we have a 10,000, we have an aircraft scale, it's 60,000 pound aircraft scale. The first test point, the specification is such that our limits are plus or minus 10 pounds on the first test point. The resolution of the device is 10 pounds, and the repeatability that we recorded was 10 pounds. So this gives us, those two numbers in that denominator give us a TUR of 0.77 to 1. Total risk is 12.1%. No matter what we do, as long as that resolution is 10 pounds and the repeatability is 10 pounds, doesn't matter what reference standard we use in the world, our risk is always going to be higher than 10%. What really needs to happen here is the resolution and repeatability need to be reduced, probably by a factor of 2, which means repeatable within 5 pounds and a resolution within 10, and a resolution within 5 pounds. We certainly, if we shift it to, the nominal value measured here was 10,000 pounds. If we shift it to 10,010, we're at the 50%. And maybe even a little more depending on how that goes on the graph. So we're going to deal with several examples here. This is our PCM, our equipment here. Typical calibration and measurement capability is 0.02% of applied force. We have 3 examples. And is the PCM accurate enough to calibrate the UT in each of the following scenarios? So if we look at these individually, and we're using method 5 here, the more conservative method, with a CMC of 0.02% and a UT resolution of 0.2 pounds, because that goes in our denominator. As long as the UT reads between 995.4 and 1004.6, the system would be accurate enough to calibrate the UT. And here I drew it like right on the line. See, we're starting the PFA here, and we still have a TUR of 21.65, but it's the location of the measurement is what matters. And here I drew it real close to the line. As you can see, our measured value here is 995.4. So as long as we're between that, no problem doing a digital force gauge 0.5% of full scale. So now we go to a 500-pound digital force gauge 0.1% of full scale. And they say, okay, as long as the UT reads between 499.7 and 500.3, the system would be accurate enough to calibrate the UT. Location of the measurement again. But look, our TUR is falling. We have a 4.33 to 1 TUR. If we said the measured value was 500.5, it would have a 50% probability of failing. But we're within the limits. Everything is good. So the next one, 2,000-pound load cell UT with a tolerance of 0.025% of full scale. So as long as the UUT reads between 1999.91 and 2000.09, the system would be accurate enough to calibrate the UT. Look here, the TUR, basically 1.25, and total risk is 1.24. So if we're keeping that total risk under 2%, we need to be between 1.99.91 and 2000. So looking at this, it's interesting. The sheet that we have, the spreadsheet, allows you to do both method 4 or method 5 or method 6. If we employed method 6 here, the graph would look, about the same. But if we employed method 6, that would allow us a lot more room to pass. So yes, if you had a PCM and wanted to calibrate load cells to 0.025% of full scale, you could do it. Both methods. You could actually do it with a 1-to-1 TUR, but you have to calculate these limits accordingly. So, and the risk accordingly. And if the risk is higher than 2%, you need to shorten those limits to make it less than 2%. So that gets to choosing the right equipment. The reference equipment chosen could affect the TUR in the following ways. It can raise or lower the TUR. Different equipment types have different CMCs, which will raise or lower the TUR. They're in this formula right here. So different reference standards can make repeatability of the UT better or worse. An example would be, we're using dead weight. That's going to be much better for the most part than hydraulic, because of the stability of the hydraulics would factor into the CMC when you do repeatability studies, reproducibility studies. Different reference standards have different resolutions. So dead weight has 0. We're not using a secondary standard or load cell. Well, a 60K load cell may have 0.15. Well, that 0.15 goes into the CMC. Changing the reference standard type will change the process, resulting in an increase or decrease in the CMC. So we're talking about this. And then the next important thing is, I get everything. So I get everything wrong. If I get everything wrong, or if I get everything right, let's say I get everything right with TURs and everything else, but I fail to use the right adapters, guess what? It's not gonna work for me. So the right adapters, send the calibration provider the adapters you use when using the equipment. So this is an example, 2 different adapters there pictured on the right over here. One customer sent in a load cell. They said, calibrate this. We said, can we have your adapters? They said, use your adapters and report what you've done. I said, really? Okay. So 2 different adapters. Either one could be used by the customer. One has 1.5 inches in engagement. The other one has 0.5 inch of engagement. There was a difference between using these 2 adapters of 59.2 pounds on a 10,000-pound load cell. We documented what we did. We noted it on the certificate that we engaged to roughly 1.5 inches. Hopefully the customer can repeat this process. But if we didn't have that discussion, and if we did not document that on the certificate, and they send the instrument to a calibration laboratory, and then they go use something completely different, right here they could have an error that throws all their tolerances off and everything they calibrate, and they may never know it. So really important to get the right adapters. So rule number 3, have the right process. The last rule requires having training program, proof of training records to validate the individuals performing the calibration or using the equipment. It's important to maintain and follow procedures that adequately support the end product performance. There should be a process in place that ensures all aspects of the standards are being carefully satisfied in the calibration process. Use of proper adapters and making sure the instrument's calibration matches how it is being used in the field or lab. So we talk about right process. So this is an advertisement for a retention link. And you see this, and right off the bat, I see a problem. So they're promoting this as a good way to accurately measure torque measurements, which it may be, but this picture is wrong. The reason it is wrong is this, to do torque, needs to be at 90 degrees. So looking at this picture and saying this is a good way to measure torque, if we do this actual calculation and we say, let's assume we have a 45-degree angle down here from the picture, the sine would be the square root of 2 divided by 2, or about 0.71. This equates to a 29% error in the torque measurement. If this picture were shot with the angle at 90 degrees, guess what? Right process goes away. Still might be some safety concerns, but all that 29% error goes away. So if anybody's doing this, just change the angle to 90 degrees and you'll be much, much better. 29% error, I don't think that's going to be acceptable to anyone at any time for a torque measurement, even on a pipe. So things to be aware of. The right procedures. Here's one: not following the ASTM standard. So you have an ASTM standard. It says per section 8.6, the loading range shall not include forces outside the range of forces applied during the calibration. Okay, that's one. So so 0 is applied right here. My loading range is 0 to 10,000, but then section 7.2.1 states, in no case should the smallest force applied be below the lower limit of the instrument as defined by 400 times the resolution for class A and 2,000 for class B. In this example, the resolution is 0.1, so I cannot use 0 as my first test point. In this example, the lowest I could go for a class A device, which is called out here, is 40 pounds. If I had 40 pounds, I could assign a lower limit of 192.3. I do not have 40 pounds. I have the first test point at 500. Therefore, my lower limit, the best my lower limit can be right here is 500 pounds, not 192.3. So this is not following the right procedures. It's in the standard. If you're going to this lab and you have lower limits that are below this, technically they are not valid. So it's something to consider. So the right calibration provider. Some calibration providers do not include enough information to provide a traceable measurement. These are common mistakes. You may or may not be doing this. I'm sure you have seen some of it. No mention of uncertainty of the reference standard. Claiming traceability to NIST and not SI. Hopefully the new standard will eliminate this. It's been, as I said, it's been an ongoing thing. We still see it. We still have requests for it. Not reporting uncertainty per point. That was a requirement of ILAC P14, the new standards requiring it. Making vague statements. I've seen meets all published specifications. So, but then they fail to mention any of them. So what published, is that every published specification? That's a heck of a lot out there. So if you're going to say, you should at least say what specifications you meet. And then gratuitous spelling errors on lots of certificates. It's usually the lack of a non-automated system or just carelessness. And when you're doing your risk, you could say, hey, I have a system as such where someone's typing up the certificates and we have a, high probability of a spelling error. What's the impact? Maybe the impact on a scale of 1 to 10 is a 1, as far as, it doesn't, as long as the data's right and you just spelled something wrong, maybe the impact's a 1. It doesn't, the customer's still getting what they need. The search, maybe you view the impact as a 3. I don't know. That's a subjective test. You need to go over it. You need to figure out what it is for your organization and calculate it. It's risk equals probability times impact, and you can go through and do it for each section of the standard. Proper adapters. I wish the standard would address fixturing and adapters. It doesn't, so here's what I have to say. Have the calibration provider replicate how the device is being used. If you fail to do this and you do everything else right, you will still be behind. Here's a situation. We have a difference. Customer sends in a device, please calibrate it. They do not send the pins, the forged pins that are being used with the instrument. If we just use any old pin, in this scenario, we have 2 different size pins that I'm showing, but the instrument is spec'd at 0.1% of full scale. So at 50,000 pounds, we're looking for 0.1% tolerance. If we use one size pin, we get 49,140. That's out of tolerance, of course, way out of tolerance. Versus if we use the correct size pins, we get 50,000 pounds. So this is actually a 1.97 inch pin over here on 50,000, and that pin is smaller. Or that pin, I'm sorry, that pin I believe is smaller on the left. So two different pin sizes could happen if you send your device in without the proper adapters, or the calibration provider does not list. We list on our cert the pin size we use. So if we use a 50 millimeter pin or 1.97, we list it. And some people will say, hey, my cal provider uses a 2-inch pin. Well, 2-inch and 197 will actually give a bit of error. It's amazing how sensitive some of these things are. So that talks about our systems, quick change type of adapters here in a cal machine. We have the clevises, the various pin sizes here. It's important to match those pin sizes with the manufacturer's recommended. So what we went through and did, we developed clevis sets with the proper pin sizes. So per the manufacturers, they're all called out. If you go to that sheet, precision machining, there's sphericals in there per ISO 376. There's lots of things. This is a big cost saving if you're running a cal lab. Big cost savings to have the right adapters, to have the right pins, one set of clevises with various sets of pins. So what we did is we went through and we looked at all the manufacturer spec sheets, and we created a big list on the link to the clevis kits that showed the appropriate pin sizes and what the manufacturer calls out. So here's something that's a little bit pretty interesting right here. Two Dillons, and if we look at this, and we look at the 20-ton versus the 25-ton, the 20-ton actually calls for a 2-inch pin, where the 25-ton calls for a 1.97-inch pin. It's counterintuitive to me that the larger instrument takes a smaller pin, but we went through and we did all this, and in the link to the sheets say what instruments they calibrate. So some things to summarize measurement risk: have the calibration provider replicate how the device is being used. Very, very important, probably the most critical. The next step is, have competent technicians. They're all important. Use the right calibration provider, but competent technicians meets a requirement per 6.2.3 of the new standard. Use the right equipment, requirement per 6.4.5. Lower your uncertainties through your calibration provider. Here's a TUR table, assuming, 0.01 and 0.5 repeatability. You really have to run the numbers for yourself. There's quite a bit of difference between labs operating on all the different TURs. This spreadsheet, like I said, you can plug numbers in. You can see if your stuff's in or out or tolerance. You can see what it means, what your calibration provider is doing. You do all that if you care to do it. So often to us, I say accreditation is not enough. Our mission is to be regarded as the best independent force and torque calibration resource in the world by providing realistic solutions and continually develop new products to meet customer needs. We also like to defy the averages and meet 100% on quality delivery and overall customer satisfaction. There's a supplier scorecard of 100%. We like to help educate our customers, provide these free webinars and everything else, so you can get thinking about why measurements, what started with the warship Vasala, why measurements matter. Am I using an 11-inch ruler when I should be using a 12-inch ruler? These are questions, and that's what happens with the different adapters. If you're not using the right ones, your ship is going to sink eventually, and that's the point I want to make. So some additional things, we have training. If this is interesting, you want a full week class, we have training that's April 9th through April 12th. That's on the website. There's more information about upcoming training and webinars that are on the site. Our next webinar is not scheduled yet. It's tentatively going to be titled ISO 376 Explained. That is a force standard. Most of Europe is using that force standard. The only thing I have to say right now about ISO 376 is it is not the same as ASTM E74. So if you're working to E4, you need ASTM E74 as a standard. If you're working to ISO 7500, you need to use ISO 376 as the calibration standard. So I'm going to open things up for questions, Q&A. I will answer the questions here. I will end the recording at this point, and then I will answer the questions after that. So, and thank you, everybody. Remember, one accurate measurement is worth 1,000 expert opinions. Love that slide. So with that said, gonna end the recording.